Hey guys, back with the second part of our momentum review, looking at numbers 3 and number 4. These also involve impulse momentum theorem. So I'm going to rewrite our equation for us. That is, the impulse is equal to the mass times our change in velocity. That's our change in momentum, which is also equal to force times time. That's how we calculate an impulse. The first one, we have a car that's going to be decreasing from 35 to 15 meters per second. And it's giving us a force. It's asking us for an amount of time. So first, let's calculate the impulse. The mass of the car is 2,500 kilograms. That's what's given to us right here. We're looking for the change in velocity. That's 35 to 15. So the final is 15. That's 15 minus 35. It's going to give us negative 20. Is equal to, well, it tells us the force that the brakes can apply is 650 newtons. And, well, it's important to note here, this is going to give us a negative number. The frictional force from the brakes is also going to be a negative number. That's negative 650 newtons times the time. So you're definitely going to get a positive number for the time, right? If the impulse is negative, that force has to be negative. They're going to be in the same direction as it is a vector. That gives you 76.9 seconds for your time. We're using this same equation, the same setup for number 4. A child is going to push his sister on a swing. It's giving us the force that he is going to exert, 50 newtons, and a time of 0.75 seconds, so we can find the impulse. It's giving us the mass of the young lady, and it gives us her initial velocity, and is looking for her final velocity after. So we're going to go into this dV, and we're going to change that a little bit. So impulse is equal to mass times change in velocity, which is equal to force times time, right? This is number 3 and this is number 4. So if we're looking at this push, it says there is 35 newtons. I'm sorry, 50 newtons. Getting my numbers mixed up. Times a time of 0.75 seconds, that gives us our impulse, is equal to mass times change in velocity. So the young lady's mass is 35 kilograms times her change in velocity. Well, we can actually write the change in velocity as final minus initial. And her V initial is 5 meters per second. So her V final minus her V initial, which is 5 meters per second, we can substitute right into that equation for our delta V. So solving for our initial velocity, or rather our final velocity, the final velocity has to be a larger number, right, to give us a positive impulse or positive momentum change. That gives you 6.1 meters per second. Now, if you just did this and same for delta V, you would get a delta V of 1.1, and then you would just have to remember to add that on to the 5 meters per second to find her new velocity. And you would still get 6.1 meters per second. It's just doing the problem in a slightly different way. Okay, I'll stop there and I'll be back with the rest involving collisions.